Okay. Number 6. Area. If A and B are the lengths of two sides of a triangle, and theta is the measure of the included angle. So we've just got some random triangle. This is A, this is B, so that means this is theta because it's included. Then the area of the triangle is A equals, this by the way is the law of sines. I don't think we got to this in pre-cal. How is dA dt related to dA dt, dB dt, d theta dt? So in other words, let's just take the derivative with respect to t. So dA dt, I would pull this 1/2 out. All right, it looks like we've got, I'm going to do this again because I've got 3 things multiplied together. So I'm going to do these 2 as a product and then by the third. So whenever I do derivative of the first, I'm going to do derivative of A, which is dA dt, times the second, plus the first times derivative of the second, which would be dB dt. All right, so all that's derivative of the first, right? Times the second. Plus the first, which we said was AB altogether, times derivative of the second. What's derivative of sine? Cosine, but you got to chain it. Theta dt. Y'all get it? Yeah. Do I have to do A, B, and C to do D? Find the rate at which R is changing when V equals 12 and I equals 2. Is R increasing or decreasing? The rate at which R is changing, so that is, and this is number 7, the rate at which R would be dr dt. Did y'all find an equation for dr dt somewhere? All right, let's go back to the beginning. V equals I times R. V is increasing at a rate of 1 volt per second, so dV dt is 1 volt per second. I is decreasing, so di dt is decreasing at a rate of 1/3. So I'm going to make it negative since it's decreasing. Amps per second. Let T denote time. Find the rate at which R is changing when V equals, so let's take the derivative here. It doesn't say at a specific time, does it? Okay. dV dt equals derivative of the first times the second plus the first times derivative of the second. And let's plug in what we know. What do we know? We know V is 12, we know I is 2, and we know dV dt and we know di dt. That, what? We know what? Yes. And di dt. Do I have everything else I need? Let's see. 1 equals negative 1/3. Do I not know R? Absolutely. Let me plug in what I know, just so y'all see my thought process whenever I go through these. dr dt is what I'm trying to find. So when you got to this point, you're probably in a bit of a conundrum and you go, well, wait, I don't know what to do because now I have 2 variables and I don't know which one to solve. But Jalen's exactly right. At this point, you would go, okay, well, is there any way for me to find, I know that what I need to find, what they've asked me to find is dr dt. So there's no way I'm going to get that without solving the equation. So is there some way for me to find R with the given information that I have? So if you go back to that very initial equation, I have V and I have I, so it tells me that V equals I times R. So I can plug those values in. So if V is 12 and I is 2, then what is the value of R? 6. So I do actually have R here in this case. So now I have 1 equals negative 1/3 times 6 plus 2 dr dt. So you see how you're kind of using everything you've been given, add to and divide by 2? And what are my units here? What's R in? Ohms. Ohms per second. Good job, y'all. Y'all ready to kick it up? Okay, so you say, oh, I'm just kidding. But might as well, right? Like a Band-Aid. Here we go. There's a picture in your book. I'll try. A lot of these, they'll give you a picture. Some of them you won't. Your picture is going to really, really help you as you go through this. Filling a trough. This is number 20, by the way. And so I have this trough. I'll try to draw it for you. I promise I try when I do this, y'all. I know it doesn't appear so. Okay, well, this is my trough with water in it. Green water. And into this trough, so it says a trough is 15 feet long. That would be 15 feet. The length is the same up here, right? It's going to be the same either way. They put it up top. Okay, 15 feet long, 4 foot across. So this is 4. Its ends are isosceles triangles with height of 3. So they say from here to here is 3. Then let me just pull this triangle out so you can see. That might help us. This is my triangular end. This is 3 and this is 4. Okay. Water runs into the trough at a rate of 2.5 feet cubed per second. So you've got this hose pipe or whatever that. So this is coming in at, what did I say, 2.5 cubic feet per minute. No, second. How fast is the water level rising when it's 2 feet deep? How fast is the water in the trough rising when water is 2 feet deep? Kind of gross, right? I always, when I think of calculus, these are the kind of problems I think about that I think everybody thinks, because they're not all this hard, but this is pretty tough. So let's try to wrap our brain around what they're asking us for, what we have, what we can find, what we don't have, what we need, all that good stuff. So I have this trough. I know I've got volume somewhere, right? Volume's going to come into play. I know that from the cubic feet. I've got the rate that the volume is increasing. Do you agree with that? Because if this is coming in that fast, that means my volume of the trough is changing. Agree or disagree? I'm just kind of trying to list what I have. So at some point I'm going to need a volume, right? Well, how do you find the volume of this? Any ideas? It's just a triangle all the way down. Whatever the formula is. I'm gonna go. Y'all tell me if you think I'm right. I don't have the formula for this. What is this even called? Triangular. So I'm thinking we do the area of the triangle times the height for the volume. Now what you would think? That's what you do for a rectangle. That's what you do for everything, right? Length times width times height. Here, if I do the area of the triangle on the end, no. Because I got to take the length into account too. Great day. I think it's going to be area of the triangle times the length times the height. Let's see. Yeah. One half base times height times length. No, yeah, so I was right. I just said the height, but you wouldn't need the height because the height is taken into account by the triangle. All right, so I'll give you this formula. The area of the triangle, so base times height times the length. And that makes sense, right? The area of the triangle times how long it is. Okay. Can we take, let's see, can we take the derivative of, and here's what I want, here's another hint to these. Sometimes you have constants, you have things that are not changing regardless. Even as other things change, that thing is not changing. So do you see something that as I fill in with water, what's not going to change ever? The length. The length. You still need me? You see what I'm saying? As the water rises in there, right? Because that's what we're looking. We want to know how fast is the water in the trough rising. The one thing that's going to be a constant as the water rises, this triangle's area is changing as it goes, right? So this is going to be changing constantly, but it's always going to be 15 feet across. That's never going to change, no matter the level of the water, right? So I'm going to consider L a constant in this as I find the derivative. Does it make sense why I'm considering L a constant? Okay. So as I find the derivative here, I'm going to look at this as a constant. You absolutely could. You absolutely could. Because it's going to be 15 regardless. Y'all okay there? So when we start, we'll say now the volume 15 over 2 base times height. Does that make sense? Now take the derivative. So dv dt, derivative of the first times the second plus the first times derivative of the second. What is it that I'm looking for? The rate that what? That's right. This, how fast is it? So I'm looking for, I need dH dt. And it says when the water is 2 feet deep. So that is my, when H is 2. Well, I still don't, when the water is 2 feet deep. So when this is 2, what will how is it changing? So how fast is it rising when it hits 2 feet? Any ideas? Because I have too many variables here, right? Do you see that? Do you see that I've gotten to this point and I go, okay, well, I know dV/dt. I don't know dB/dt. I do know H. Do I know B? No. And dH/dt is what I need. Too many variables. I know that I need this one. So I have to figure out a way to find this one and this one. Any thoughts? What if I make a ratio? Would that make sense to you? What if, do you agree that the ratio, as this water rises, the ratio of the base to the height is going to remain the same? Does that make sense? So currently in my whole isosceles triangle, it's 3 to 4, right? Is that right? Or is it, yeah, 4 over 3. Agreed? Knowing that, could you then solve maybe for B? Because you know the height, right? So if the height is 2, what's the base? Y'all can do that much, right? So this came from my original triangle, right? This is the height, I mean the base, this is the height. So I said, because that's the ratio of that triangle, as this water rises, that ratio is going to stay the same. I started with kind of a hard one, I'm sorry. I should have started with this one. It's okay. Are y'all following so far? Right now, you probably wouldn't. This one was a little hard to start with. This one's tough. You'll start to the more we do, you'll start to recognize which variables are constants, and then it makes it easier as you take a derivative. I'm going to multiply by 2 and get 8/3. Okay, I'm going to plug that in for B. That's still not going to help me. I got to back up and punt. Do you see why? Too many variables. I'm going to go back to what I was doing with optimization. I'm going to come back to this equation, and I'm going to write it in terms of just one variable. Since now I've come up with this, I'm reasoning through this as I go, y'all. I didn't work this ahead of time. This is how I reason through them. Okay. Do you see where my problem lies? Do you see why I got here and went, wait, I can't do it this way? I can find B. I know I need dH/dt. This dB/dt is throwing me for a loop. There's no way I'm going to find the rate at which B is changing with the way everything's set up now. Do you see that? So I'm going to go, wait, I can make this problem infinitely easier. Because now that I thought about doing the ratio, well, if B over H is 4/3, I need the HDT, right? I'm going to change this B and write it in terms of H. Just like I was doing with optimization. You see what I'm saying? So that I only have H's in my equation. So if B over H is 4/3, B is 4/3 H. Do you agree? Okay. So now my volume equation, watch how much easier this becomes. I made it way harder, I'm sorry. 4/3, actually, like 15 over 2. Base is now 4/3 times height times height. That is a much easier problem to take the derivative of. Do you agree? I agree. It just is. So my volume is actually, let's see, that's 2, that's 1, that's 1, that's 5. 10H squared. Now dV/dt equals 20H dH/dt. Now I can plug in the things that I know. dV/dt is, what did we say? 2.5. When the height is 2. Wow, look how much easier that was, y'all, if I omitted all of that. Yeah. We'll just finish this one out and then I'll let y'all digest it a minute. What's 2.5 divided by 40? Is that 1/16? That's what that little blue answer is in the book. It's going, please, please, please let us be right. What is it? What is it as a decimal? What did you say? I'm sorry. And I am in feet per minute. Now, in context of the problem, let me explain what this means, because you will be asked sometimes to explain, and you can get a whole point for just knowing how the answer applies to the problem, not even count the answer itself, right? So if you understand what it is you're finding, at the exact moment when the height is 2 feet and the volume is increasing at a rate of 2.5 cubic feet per minute, the height of the trough, of the water in the trough, is increasing 0.0625 feet per minute. Sorry I made it harder to start with, and then y'all just were done after that. So whenever I got it written down in one variable, so okay, lesson learned, if you can ever do that, try to get it written down in one variable, which we practice with. I don't know why I didn't do that to start with. Let's try another. Let's try one, maybe not quite. Oh, here's a good one, kite flying. Y'all ready? Shadows and kites all the time. Ridiculous. Okay, this is number 14. Flying a kite. Inga? Ingi? I don't know. Flies a kite at a height of 300 feet. She's flying her little kite. The height, it says flying a kite at the height, so I'm assuming that's the height down to the ground, right? 300 feet. The wind carrying the kite horizontally away at a rate of 25 feet per second. So I'm thinking that means that this 25 feet per second. This is traveling that way at that rate. Does that make sense? And I'm thinking this is going to be some type of trig problem because the ground always makes it perpendicular to your height there. Okay, let's finish reading the problem. How fast must she let out her string when the kite is 500 feet away from her? So, I don't know. What do y'all want to call this? This string, we'll call it S. So we want to know when S is 500, what is the SDT? What? How fast must she let out the string when the kite is 500 feet away from her? How do y'all interpret that? I took it as the string, but what did y'all? Abby says the height down across the ground. So you're saying you think this is 500. That's not how far she is from the kite, though. I don't know. I don't know. I'm just guessing how I read it. Want me to tell you? You want me to tell you why I think that the hypotenuse is 500? Because if the hypotenuse, and I'm just guessing, I haven't worked this problem. If this is 500, this is a 3, 4, 5 triangle, this would be 400, right? It sets me up for a perfect Pythagorean triple in my triangle. I don't know. I know the answer. How fast must she let the string when the kite is 5? I still say it's, now you will listen. If you're on an FRQ type situation, they're going to be way more specific than this, and that will be taken into account, and you will know. I still say if she's 500 feet away, but I get. Oh well, that's interesting. Well, let's work it both ways and see which one gives us the answer in blue. It has to be that one because if it says, how fast must she let the string out? Well, maybe not. You're saying if this, see, I'm thinking this is A and this is B. This would be C. We'll go this way first, and then if we don't get 20, then we'll come back and work it the other way. Okay, help me set it up. What do I need? I need some equation that's going to relate ds dt, or dc dt, whatever you want to call it, to S, and I have A and B. And because I have A and B, I was able to find that hypotenuse side, right? Or vice versa. Any ideas? Well, this one's Pythagorean theorem. A squared plus B squared equals C squared. So we're trying to find ds dt. Right? We're trying to find how fast is she having to let the string out to keep up with the wind speed coming across here at 25. So that's what we're in a conundrum about. The problem told me that you want to know how fast must she let out the string when the kite is 500 feet away. So that's what we were kind of, don't know if the 500 feet away is this way or the 500 feet is away from the base. I say it's this way. What do you say, Alex? Well, clearly everybody thinks the opposite of me. What do the solutions say? Somebody pull the solutions before we work it the wrong way and see how they set it up. But don't cheat. Don't look at how they did anything. Just look at how they set it up. I know, but y'all are making me. I could very well be wrong. I've been wrong many times before. This is 4, 6. I hope they have a picture for it anyway. Maybe I could photo map it. Okay. Yeah. What do you say, Jalen? S equals 500. They used S. Where's their S, though? The ground or the string? Huh? Oh, so I was right. Woo! Okay. I have no confidence in myself. Okay. Okay, that's good to know. Woo, I was just going to quit if I was wrong on that one. All right. I need to relate all this stuff some way. Give me an equation that relates something. That's exactly what I would do. A squared plus B squared is equal to, we called it S, it could be C, whatever. It's an easy equation. We all know. We know what S is. I told y'all that was that Pythagorean triple. When I saw that 300 and 500, I was like, what can we do? I don't really need to know how A is changing. Do you agree? I don't need to know how the height is changing. I'm thinking about whenever I take the derivative, right? If I take the derivative the way it stands right now, I've got 2a dA dt, 2b dB dt, 2s ds dt. I need these two, but I don't need anything about the way this is changing. So can I write this one in terms of another variable, is what I'm thinking. Okay, so this is A. That's the height of the kite, right? And okay, so let me write, this might help you. What do I have dB dt, B, A, and S, and I need ds dt. Yep, because that's the wind blowing. That's okay. That's the wind blowing, right? So I don't want, whenever I take the derivative, I don't want dA dt in it because I don't have any use and I don't have any way to find that right now. So what I'm going to do is rewrite this equation with only S and B. Does that make sense as to why I'm doing that? Okay, so I think if I know that A squared plus B squared equals S squared, well, A is not going to be a constant because as it moves, the height's going up. What? That's the rate that that's the wind blowing horizontally, is what that is. So how could I rewrite this? I know that S is 500, but it's not going to stay 500. I can't do that. Can't plug it back. I need another equation. 2a dA dt plus 2b dB dt. Well, why can't I do that? Why can't I say that this is the square root of s squared minus b squared squared plus b squared? No, that's not going to work. It's going to give me 0 and 0. Terribly. Okay, so if we let a be a constant, then everything makes way more sense. Because that means that whenever I do derivative here, that's just 0. Gosh, I don't agree with that. When is the wind ever just blowing? I guess because it says horizontally. Okay, so my derivative is really 2b dB dt equals 2s ds dt. Does that make sense? Well, because if you take the derivative of a constant, it's 0, right? Now plug in what you know. Yes, they're looking at a as a constant because they're saying the height of the kite is always 500 or 300 feet off the ground. And the wind, when the wind blows and you let the string out, that it's just going horizontally and it's not going, which is dumb, but okay. Not real to life, I suppose. So B is 400, so 2 times 400. That was supposed to be the hard part of the problem, was knowing to find it to be 400. dB dt we have, yes ma'am. Pythagorean theorem, so 300 squared plus b squared equals 500 squared. S is 500, and ds dt is what we're looking for. Please, Lord, sweet baby Jesus, let this be 20. It is feet per second. I have failed at 2 problems now. Right, day. Want to do another one? Okay. Let's do 16. I bet you will. You'll be able to start them at least. I find it helpful if I come over and I list, what do I need? What do I have? You know what I'm saying? That way it kind of gives me an idea of what variables I need to relate back and what I need to get rid of and how to find an equation. Let's do 16. Well, if it makes you feel any better, these are hard even for me. You see me struggling. Sand falls from a conveyor belt at a rate of. So I've got this conveyor belt with the sand that's falling off. At a rate of 10 cubic meters per minute on top of a conical pile. You know, like if you drip it off, it just makes a cone. You know what I'm talking about? Yeah, it's like a cone, like an upside down waffle cone. You know what I'm saying? Like, okay. Does it say that word? Conical. Yeah, it says, okay, so it says, sand falls from a conveyor belt at the rate of 10 cubic meters per minute onto the top of a conical pile. Right. Greer's getting really worked up about this. What is your problem? Okay, the height of the pile is always 3/8 of the diameter of the base. Okay. How fast are the height and radius changing when the pile is 4 meters high? So I need how fast is the height changing, dH dt, and how fast is the radius changing, dr dt. When the pile is 4 meters high, so what do I have? I have the height being 4 meters. Okay, that's all we have. Oh, but you have to give your answer in centimeters per minute, even though the problem's written in. Oh my gosh, I just went between two different problems. No, I didn't. No, I didn't. Okay, the next one is in. Okay. No, but I have never seen them do that before on an exam. Right. They're 100 centimeters in a meter. Move the decimal twice. Remember King Henry died by drinking chocolate milk? Okay. What do you think? I see a DVDT in there. That's the very first thing I see. So I know. I'm gonna also put we have DVDT. Say again. There you go. All right. So if you rewrite the diameter, we know that diameter is equal to 2r. That's going to relate my r back because I need a dr dt, right? So instead of saying that the height is 3/8 times the diameter, I'm going to say the height is 3/8 times 2r, which is 3/4 r. Everybody okay? Now, let's look at what we need, let's look at what we got, and let's see if we can find some type of equation that's going to help us write everything together. Let's focus first on, I don't know, which one you want to do first? The HTT? Okay. Let's look at this one first. So DHTT, H, dVdt. How can we relate them? Well, what's the volume of a cone, first of all? Because I've got a volume here. I would say 4/3 pi r cubed, but that's my answer for every volume all the time. You were right, Caroline. Be confident. All right, so having H dVdt, I'm thinking whenever I take that, I need one of these variables gone, right? So I need something that's going to relate H and R. I already have what H equals. Look at this equation we just came up with. Okay, so look at what you have. Let's get them written down in just one variable so that whenever I plug in, I can solve for what I need to. Okay, so think back to optimization. Remember whenever we said, what do we have? What do we need? How do we get it in just one variable? We're thinking the same way here. Okay, how do I get it just in that variable? So since first I'm looking at dH dt, I'm going to write this just in terms of H. Well, I know that H is 3/4 R. So I'm going to say that volume is 1/3 pi r squared 3/4 r. We will after we take the, this is this is kind of after you take the derivative whenever you're plugging in, because you want to know what's the rate at the instant that the height is 4. All right, let's clean it up a bit. Volume is 1/4 pi r cubed. Everybody okay? Now take the derivative. dv dt is equal to 3/4 pi r squared dr dt. I know that dv dt is 10. If the height is 4, that means the radius is, height is 3/4. Oops, let's solve it the right way. Height is 3/4 r, so if height is 4, what's the radius? 16/3. So y'all are now like, let's just go back to optimization. It really wasn't that bad. It was pretty bad. Two hardest things we do with derivatives right here. All right, 3/4 pi 16/3 squared dr dt. I don't know. Somebody tell me what you get. I was sitting here trying to do it in my head. Funny. 16 cubed, 16/3 squared times 3/4 64/3. Now I'm going to multiply by the reciprocal. So I'm going to do 10 times 3/64. The pi actually goes to the bottom. Meters per minute. Oh, this is a calculator problem. What's the answer for this one? I don't know if that's what they got or not. I see a 32 pi. Let's see, they got 11 point. Well, they're in centimeters too, so I have to multiply by. I don't know. I don't know about their answer. That's what I got. Is that what y'all got? Yeah, we got to go back and do DHCP now. So now instead of solving this way and replacing the h, now I'm going to replace the r. So r is equal to say that one more time. Yes, you could actually, since you have dr dt now, you absolutely could. That's a good way to look at it. Good job, Abby. That is good. Did y'all hear what she said? Since we now have drdt, could you come up here to this equation and say, well, dHdt equals 3/4 R drdt? And the answer is yes, you definitely could do that. Since now you know drdt. The problem before was we didn't know drdt. Now we know drdt, so we could do that. Nice way to look at it. Yeah, because we did plug in at that instance. So dHdt would equal 3/4, what was R? 16/3. And drdt was 15/32 pi. So whatever that comes out to be. And remember, if you're on I don't know. There you go. Right. It's just 3/4 drdt. Yeah. If you're on FRQ, you can stop right there and leave it like that. You can plug it in a calculator, you can leave it. Tomorrow's not the day that I'm not going to be here. She changed it to Thursday, so we'll be here tomorrow. Well, I'm thinking, I don't want to leave y'all, I'm going to leave you a review on Thursday, but I don't want to not be here a day to answer your questions. So I think that we'll do the test on Monday. That'll still leave us Tuesday, Wednesday, Thursday, Friday, Monday, Tuesday, Wednesday to review. I'm talking about like your exam for, not exam, but like Thursday and Friday are the exams on the half days. That's the day we have to give. Oh, yes, yes, because y'all are exempting your exam. So I'll give it to you Wednesday. Yes, yes. Yeah.